So we will start today a new chapter in data structure. That is, till now we have discussed actually different type of algorithms for solution of a problem, but we have not yet thought about what is the best one and what approach is the worst one. So to do this, what actually we have to do is what we call uh, just last let me write it. What we call complexity analysis. Okay, so so we will understand why this complexity analysis will be needed with an example. You see, when we write a program, uh, some program is there, suppose maybe factorial of a number or something like that. So it's a set of instructions, and what this program, if we consider it as a black box, something like this. Suppose this is your program. This program has some input and program produces some output, right? Now see, that means this program is actually have a mapping from input to output, some input output. If I consider this program is a program of a square function, so if the input is 2, output will be 4. If the input is 4, output will be 16, and so on, right? So that means I can say that this program is basically is a function, right? Something like this. So if I assume that I have a function y equal to fx, this x is the input to the program and y is the output of the program, and this f is represent the program itself, which is taking your input and converting to some output, right? So that means one thing is sure that every program is actually some function. Well, mathematically I can say that. So let's take two functions that represents two different programs. For example, say function 1 is function 1 with n. N is what? N is number of input. Okay. So suppose the presentation of this function 1 is something like 100n. Okay. And this f2 with n is something like say n square. Okay. So if the representation of the two program by these two functions and their definition is something like this, then let's try to compare the performance with some unit for different values of n. So let us do it. If we write that we have two things, here we have f1n and in another side we have f2n, and here we have actually number of input, that is n. So if the n equal to 1, this f1n will give 100, right, because it was 100n. But f2n will also give 100. No, I'm sorry, it will give 1. You see, it is giving 1. 1 square, it is 1. Some unit. That may be microsecond, maybe nanosecond. So assume that they are having the same unit. Okay. So maybe microsecond or maybe nanosecond. That is not important. Now, if I increase this number of input, n equal to 1 to 10, then what will happen? It will become 100 into 10, that is 10 to the power 3 unit, and this will become 10 in 10 square, n square, right? 10 square, so that means 10 square, right? Now let's go for n equal to 100. What will be the value? 100 into 100, that means 10 to the power 4. And this one for n square will be same again, 100 square, that means 10 to the power 4. If I increase more, say 10 cube, in that case 10 cube into 100, 100n, so 100 into 10 cube, that means it will become 10 to the power 5, and this become 10 cube square, that means 10 to the power 6. If I increase more, 10 to the power say 5, so it will become 100 into 10 to the power 5, that is 10 to the power 7, and it will become 10 to the power 5 square, that means 10 to the power 10. So if we go on increasing, you see the difference between these two values is increasing as the number of n increases, right? So that means I can once say that if you draw the graph that shows the performance of these two programs for different value of n, how it will look like? It will look something like, we have a graph over here. This f1n will look something like uh, maybe something like this, f1n. This is f1n. F2n will look something like, this is f2n, you see. Why I have said this one? Because you see, up to n equal to 100, actually before n equal to 100, this was lesser than this one, right? At n equal to 100, they are equal. And beyond that, as n increases, the graph, this f2 become very, very large than f1. So f2 can be something like this, where the point, cut point, is actually where n was equal to 100. And before this 100, this was lesser than f2, f1. So, from this particular example, what conclusion we can draw? Just a minute. What conclusion we can draw? We can say that you cannot compare two functions with smaller number of inputs. They may, your decision may fail. So the algorithm should compare two algorithms should compare with very large number of inputs. Is that clear till now what we have discussed? Okay. Now see, this from this statement a concept has came, what we call asymptote. What is asymptote? Mathematically, asymptote is the curve which approaches to the same as another curve or a axis, but doesn't ever meet to the axis. For example, if you take a graph something like this, just let me, and if you take the function as say y equal to 1 by x, okay, and if this is your x-axis and this is your y-axis, you see your curve will be something like this. Because what this particular curve is saying, if you don't even know about the function, then also from this curve, what actually we can draw conclusion that as x tends to infinity, 1 by x is approaches to 0. Right? Now, that means, you see, if you take another example, like say we have another curve, something like some straight line, this is not an asymptote. Because as x increases, the value of the y of this curve also increases and goes to infinity. It doesn't have any way to meet with any axis or any other curve. But here, you can never say that x will be equal to 0. What we can say? That if x tends to infinity, then it can be 0. You cannot, this is what, we call asymptote. So, here also we have seen that two algorithms should be compared with very large inputs. Similar thing we can find from this particular example, that when x is very very large, then only you can understand what is the behavior of this curve, that is almost 0. But when x equal to say 1 or 2 or 3, then something like x is 1, then the value of this particular some point in the curve is not 0, it's something very big, y, right? So now let's try to understand what are the different type of situation possible in case of in this asymptote. You see, the first one that is possible is what we call big O. The notation that we use, what we call big O, to express the asymptote for some particular class of problems. For example, consider this particular situation. Suppose one curve is something like this. This is one curve, say Fn, and another curve, suppose, is given something like. Okay, and this is, I'm sorry, uh, hmm, this is your, sorry, I'm sorry, it should be your GN. I had a mistake. It should be GN, another function GN, and this is representing a function Fn, your program. So this is X. Now this particular point is what we call N0, which is the threshold. So if we are able to write a equation something like Fn is lesser than equal to some constant value multiplied by the function Gn for some, if it cross some threshold in 0, I mean n greater than n0, then we can say uh, this Fn is a big O of Gn. So what actually we are doing? We are saying that here you see this particular Gn is the asymptote curve. So we can say that this function Fn can maximum reach up to Gn, but it will never touch this particular curve, and even it will not go beyond this. So that means we are trying to specify the behavior, the maximum behavior of my program with respect to a particular class of function, and that is represented by this Gn. So what I am doing actually, I am actually specifying the performance of my curve or my program in this region. Any doubt you have till now? Hello. You see, I am Fn is my program. Fn is representing my program. Okay. And Gn is another reference function with respect to I am comparing. Okay. So Gn is basically, a class of function. Okay. So why okay. So let me tell you more about this. So what Gn actually we are considering is a class of function. What is an example of this? For example, let's take a situation something like this. Suppose we are considering a program. Consider a program with linear time. So if it is x-axis, if it is y-axis, suppose your program is following, having a function is basically your y equal to 1 by 2x. So it will be something like this. This is y equal to 1 by 2x. If you take one more curve, y equal to another, let's take another curve. This is y equal to x. Let's take one more curve. Y equal to 2x. So if you compare these two curves, these three curves, apparently you can say that these curves are different. These curves are different. They will reach to in three different directions. But assume that x is super large. X is, assume that x is su super large. So x may be 10 to the power 19, something like this, which is towards infinity. At this situation, that means you are actually zooming this particular curve when x is very large. At that time, we will see all these y's tends to infinity, right? So if x become very large, that behavior of these three curves will almost look like same. So basically, we are not comparing with a specific type of. So actually, what we can say from here, that all this curve is following a curve of a linear time. So we are not specifying a particular type of curve exactly. We are actually specifying a class of curve, or we can say a class of function. Obviously, you can say, what is the difference between this? Uh, uh, if I write big O of 1 by 2x and big O of 2x, where is the difference? Why we will not think about this constant part? The reason is that this constant will have a very adverse effect, very small effect, if x become very large, because that is what we are considering, that we must take for a very large input. That also we have seen from this example, that the behavior can be only understood, behavior of a program, when your input is very large. For example, you cannot compare selection sort or difference between selection sort and merge sort for some 10 number of, whether number of data is 10 or 100 or 1000. You can understand this sorting when you have trillion amount of data. For example, Facebook. You are searching a particular friend and there are actually millions of users. Among those millions of users, millions number of input data, how much first Facebook is actually giving you the exactly your friend's name or the profile, that is important, not with only 10 or 20 users. So basically, in complexity analysis, we are not going to compare with an exact type of function, something like half of x as 2x, we are actually comparing with a class of function. And all these three different curves are representing a linear class of function. Similarly, this Gn is representing a class of function that may be n square, maybe 2 to the power n, maybe log n, or maybe something like that. So we are saying that my program is restricted within this class of function if it crosses threshold n0. In that situation, I can say the function is equal to big O of the Gn. So this is following. Big O reason is that this function is never crossing the curve of this Gn. So this is what we call asymptotic upper bound. So we are restricting the upper bound of my performance of the program with this, with respect to a class of function Gn. Am I clear right now? Okay, just a minute. Now, similarly, another situation is there. So this is what actually we are discussing. Big O. Similarly, another we have, that is what we call big omega. Big omega. What should be? Suppose we have another situation, something like this is your x and this is your, not x actually, we consider n. This is your time. So we have suppose this is your Gn, and your Fn looks something like, suppose this is 0 Fn. So in case of big omega, and this is your n0 obviously, we can write that if there is a constant c for which we can write the equation something like Fn is greater than equal to c of Gn for n greater than equal to n0, then we can write Fn is equal to big omega of Gn. So what actually we are doing? We are saying that we have a class of function Gn, and I'm saying that the performance of my program will not go beyond this Gn. I mean, will not go down to this Gn, below this Gn, after the number of input become greater than equal to n0, minimum number of input. So this is a threshold. So here, just like threshold in my example was 100, this was my threshold, right? Similarly, the threshold is considered here in 0. So what actually you are doing? We are restricting our performance of our program with respect to this situation. Something like this. We are saying that performance of my program will be at least follow this curve or maybe more than this. We are not sure that up to how much. We are not restricting the upper bound. Right. So here what we are actually restricting? We are restricting the lower bound of my program with respect to this class of function gn. So this is what we call asymptotic lower bound. Am I clear? Okay. So there is one more class of actually function. There is one more. So let's write it. That is what we call big theta. So what is the situation in that case? For example, this is your n and this is your time, and suppose we have a function something like this. Suppose this is your fn. Okay. There is one function. Say this is c of gn. By the way, I had a simple mistake. Here c should be multiplied. Also here c should be multiplied. Because it is saying lesser than equal to c of gn. And take one more sorry, take one more curve, something like okay. May not be true in this situation. May not be so easy here. For example, it can be something like this. This is a C. This is C1 of Gn and this is a C2 of Gn. Okay, easy. We are having the same function Gn over here, just constant air difference. So if a situation happens something like this, that and this is your n0, because if you write n0 here, then it will not be true. So what we can write that this we have fn in this in between, and fn is less than equal to c2 of gn, but which is greater than equal to c1 of gn. Right? I'm sorry, লেখাটা ঠিকঠাক হলো না. c1 gn less than equal to fn less than equal to c2 gn. If you are able to write, then we can write if n is equal to uh, big theta of g. So what actually we are doing? We are saying the performance of my program is not go beyond the class of function multiplied by the C2, this particular curve. Even the performance of my program will not go beyond below this particular class of function. So what actually we are doing, we are actually restricting the performance of my program within exactly this region mathematically. Right. Right. Sorry. So this is what we call asymptotic tight bound. First was we have lower bound, then we have upper bound, and this tight bound is actually mixture of lower and upper bound. But for the same class of function Gn, remember, the class of function has not been converted, changed. Am I clear? Hello? Hello? Okay. So now sometimes these type the short note come in your exam. I mean about this three different notations. Other than this big theta, big O, and big omega, we also have uh, small small o, sorry, small o, small uh, omega, and small theta. You know, they are not much different than previous O, big omega, and big theta. Only difference is that with respect to the equation, here we are considering equal to, lesser than or equal to. Since in case of small cases, it are these are strictly lesser than or greater than. There is no equal. That is the difference. Okay. The other concept are same. Anyway, so maybe these three cases will not come in exam. I'm not even discussing this one also. So now what we will do, we will basically try to realize how we can find the complexity of a problem. For example, there is a problem is given to you, something like a program is given to you for I equal to say 1, I less than equal to say some value, say 1000, and I plus plus, and it does some job, some instruction, some two instruction is present. Okay, and then we have one more instruction, but two instruction, and so this is your program. Okay, so this is your statement 1. Here the statement 2, and here statement 3, and here we have statement 4. Okay, so this statement obviously take a constant amount of time to execute, right? So suppose this is time to execute is C1, the time to execute statement 2 is C2, the time to execute statement 3 is C3, and it is C4. Now see, the total time taken by the program with n number of input will be what? What you can say? That I can see that if this loop run once, then the total time taken to execute the loop will be C3, sorry, C1 plus C2 into 1. because loop has run one time. And you see, if the loop run 1000 times, I'm sorry, if the loop run once time, if n equal to 1, uh, this is my question. So if n equal to 1, at that time, what will happen? C1 plus C2. You see, C1 and plus C2 is also another constant, right? You can assume. So suppose C1 plus C2 equal to C dash. Okay. So that means if n equal to 1, it will take C dash into 1 plus this two constants. Two constant as a whole I am considering C. Okay. C3 plus C4 is suppose equal to almost equal to C. I am considering. So for n equal to 1, it is taking C dash into 1 plus C, this amount of time. When n equal to 100, then what will happen? It will become C dash into 100 plus C. So basically this one we can generalize as T of n will be equal to C dash dot n plus C, right? So now when n is very large, for example n is 10 to the power 10, if n is equal to 10 to the power 10, at that time this Tn will be 10 to the power 10 multiplied by C dash plus C, right? Now obviously this in real situation this C is very small, right? C is very small. So I can say that with respect to 10 to the power 10, the C is very small than 10 to the power 10, right? So that means this C is become almost negligible with respect to the value of n. That's why for higher value of n, for higher value of n, we can ignore the constant terms. So ignore the constant terms means we can ignore this C. Fine. So now that means I can say that Tn will be equal to almost 10 to the power 10 C dash. Now what is C dash? C dash is again a constant value, right? So this is obviously n. This is not 10 to the 10. This is what our n is. So you can say that it is equal to C dash n. Fine. Now what is C dash is? C dash is a constant. As we have seen here in this example, that whatever the curve is, since all the curve is multiplied by some only constant value, in this case it is equal to 1 into x, so 1 is constant, here half is the constant, but ultimately they are representing same class of function for a very large value of x. That means here also you can say that this Tn, this particular curve is a curve, is a linear curve. I can see there is no square term, and a linear curve where it is multiplied by a factor C dash. whatever the factor doesn't matter, the class of the function will remain linear in this case. So we can say that this is actually will follow, this Tn will follow an order of the class of function where fn is, you can also write not like this, a class of function big O of fn where fn is equal to n. So as a whole we can write Tn will be equal to big O of n. So my program is following a class of function, a class of linear function which is n. If you multiply some factor with this n, it doesn't change the class of the function. That's why we omit that factor. We have omitted this c dash and we are keeping only the variable term over here. So tell me, is this clear to you? What trying to say? Yes, obviously, as we have seen in the previous case over here, is that you see I have three different curve over here, right? Three different line, straight line. One is for y equal to 2x, one is for y equal to x, and one is for y equal to half x. But when x is almost towards infinity, at that time, that means just assume that you are super zooming the axes and x is becoming almost towards infinity. So at that time, what will be the value of y for this three different straight line? Will be almost infinity. Hello, will be almost infinity. So that mean whatever the factor is multiplied with the variable x doesn't matter for a very large value of x. So that means for a very large value of x, the three different straight line are representing same class of function, that is x, a linear class of function. We are not exact that, as we are saying that we are with in this particular analysis phase, our goal is not to compare with a specific type of curve, specific type of function. Our intention will to compare with a class of function. Okay, so here if it is you don't really know what does c dash mean. In c dash mean can be 1 microsecond, it can be 1 nanosecond, or anything. Whatever, maybe 10 picosecond also, or maybe 100 picosecond. Whatever it may be, but it is a constant value. For a very large value of n, this particular thing doesn't have any significance. This c dash is not going to change the class of function of this particular expression, right? The class of function will remain linear. So we take only the class of the function. That's why we have represented in this way. Is the doubt clear? Okay, good. So now let's take one more situation. Something like, suppose we have a program for I equal to 1 to n, some value n, and there is two statements, statement S1 and statement S2 presented over here as we have seen. Then statement 3, statement 4, statement 5, and then again we have a for loop I equal to 1 to say n again. Okay, and for j equal to 1 to m, some statement 5, 6. That's all. Okay. So my question is that now here, what will be the time complexity that is following this particular program? So let's first write down the simple equation that is representing the function Tn, that is representing the time taken to execute the program with respect to n number of inputs. What you can say? You can say that it will be S1 plus S2 dot n plus S3 plus S4 plus S5 plus, you see, when we analyze the complexity, we don't differentiate with respect to this n and m. Okay. So assume that this value of n is 10 to the power, say 10 to the power 5, and this value of m is 10 to the power 6. There doesn't have much difference. We always consider a large value. So we consider that they are almost same variable. So that means you can say that it will be S6 into, it will become n into n, that means almost n square, right? So let's write it in a compact way. So suppose this is one constant value C1n plus, for this 3 we have a constant C2, then this one is another constant C3 n square. Now see, so now question is that here we have this is constant, this is representing linear class of function, and this is representing quadratic class of function, right? So now question is that, till now what we have discussed all actually dealt with a particular class of function, but here the program that I have written here in the left side is representing a mixture of two different class of functions. So which one I will take? Is my program following linear class of function? Is my program following quadratic class of function? I don't know. But try to imagine, as we are saying, that a very large value of n. So if you compare this C1n and compare this C3n square with a simple curve, if C1n is this, if it is C1n, C1n square will be something like this, C2n square, right? Because as n increases, this particular n square will become dominating on n, because n is n and n square. When n is equal to 1, they are same. When n is equal to 10, this is 10 and this is 100. When n equal to 10 to the power 3, this is 10 to the power 3, this is 10 to the power 6. So you see, as n increases, n square starts dominating n. So that means with respect to this class of function, if you take among these two different terms in the function, this C3n squared term will start dominating this term for a very large value of n. So for a very large value of n, the effect of this C1n term become negligible on the effect of C3n square, right? And obviously C2 is always negligible because it is constant. Whatever the large value of n doesn't matter, C2 will remain same. So that's why we always consider in a function the term with a higher order. That is why we can say that this Tn will follow a class of function that is uh, C3n square. But obviously C3 I will not keep over here because in the same way again the n square is dominating n. This n square will dominate also C3. So here I should write we go of n square. Am I clear? So just a minute, I am coming in a moment. Wait for 1 minute. বলো মাছ একটু আছে না দেরি আছে 11:30 11:30 12টা নাগাদ বেরোবো 12টার মধ্যে একটু পড়ে দাও 9:30 পড়ে দাও না না ক্লাস আছে 10:30 থেকে আবার আমার Hello, am I audible? Okay. So is this clear to both of you? Tell me first. What actually I am trying to say? Okay. So now let's jump to the different algorithms that we have discussed till date. So for example, we will start comparing with the sorting algorithms. So how the sorting algorithm look like? Let's take bubble sort. So in case of bubble sort, uh, what how we can define this function Tn? You see, if you closely watch the bubble sort what it was, for example 2, 1, 7, 3, 4, 9, 6, like this, what we do actually we compare these two locally, right? Then these two, then these two, like this. Two positions locally till end, and maybe we swap in between them if required, right? And ultimately, after when we come at the end, a set is completed. This is set 1, suppose. We get a set data here, and that we use to start from the beginning in this way again for the second set, right? And what we have found? After set 1, in the right hand side, we have the minimum or the maximum number present. So, in the case of set 2, we go up to this one, not the whole set. We check up to this one. And we get another set where the first two minimum or maximum number we got, and we start for set 3. And we go up to this one because that is enough, right? And in this way we get last 3 maximum number, right? Can you remember what I'm saying? Hello? I hope you can remember bubble sort at least, I don't, I'm just assisting you to make it more, just assisting you, if you forget bubble sort, that is very unfortunate. Okay. And Priyanka, is it okay? Okay. So, uh, that means in case of bubble sort, what we have actually, the logic is something like we have a for loop for I equal to say some 1 to n, suppose, and we have another for loop in over there 1 to something n minus 1 or something like that. I'm not writing exactly what it was. And here we have a comparison, right? If the comparison is true, then we have swap operation. Now, before we proceed, let I should tell you one more thing about analysis the program. That is, there are three different cases actually. You know, three different cases on the basis of which you can analyze the complexity of a problem. The first one is called best case. Second one is called worst case, and third one is called average case. Now, what's the best case mean? The input combination is best. The way by which you are getting the input is best. Here, the input combination is worst, and here the input combination is average. So everything depends on input. For example, the best case scenario of a sorting algorithm is the data is already sorted. That you are trying to sort is the given set is already sorted. In that case, obviously, the time will be taken minimum one. In the worst case means actually, the data is not even sorted, and not even, you know, single data is there which is sorted in between themselves. Let's take a best case, worst case example in case of say searching. If you consider a linear search, what is the best case scenario? Can anybody tell me? Hello. Priyanka, can you tell me? Hello. Hello. Priyanka is not there. I can't see actually. Just a minute. Then let me check it. Just a minute. No, Priyanka is there. Priyanka has some problem on. Priyanka, can you hear me? You can do one thing. You can just, uh, I mean, leave and then join. Maybe you have some network problem. I don't know whether you can hear me correctly or not. Okay, I can hear you. Is he? Have you understood? I mean, okay. Let me check. Priyanka will join the meeting again. I hope. Yes. Priyanka. Okay. So, tell me what is your opinion about the best case situation in linear search? Again, some problem is occurring. Okay, okay, Priyanka, you have some problem in your side. You have to fix it later. You just off your microphone and we will let me tell you. So as Prabhu was saying that best case scenario for a linear search is the data is present as the first element. But what is the worst case scenario? Worst case scenario can be something like the data even not present. You will search till entire array, but data is not even present. Okay. So we not only consider the best case, we also consider the worst case scenario. So depends on our requirement, we actually check whether what is the time complexity for a worst case scenario input, what is the time complexity for a best case scenario input. Okay. So in this case, generally we always consider this worst case. This is very important. The reason is that we always check what is the behavior of the program with respect to a very bad input. If the program behaves correctly or very efficiently for a very bad input, then it's natural that for best input or an average input, the program will behave better than others. If I say that I have two programs and if I find the time complexity in worst case is, in case of program 1, is better than time complexity in worst case of program 2, then naturally for a best case or an average case, the time complexity will be better. The time to execute the the program 1 will be better than program 2. So generally we always consider worst cases. So in this case also we are considering worst case in case of bubble sort. So in worst case means somehow this condition is always true. If it is really worst case, condition will be true always. If the condition will be true, then this set of statement for swapping will execute always. Now question is that how much time? Let's try to write it. You see the time taken to execute by n number of input in bubble sort. You see when n equal to 1 for the first set, we are actually going n number of comparisons, right? N number of comparisons with respect to comparison 1, comparison 2, comparison 3, comparison 4, something like this. So since we have to traverse till the end, we can assume that we have n comparisons, because in worst case we are considering that condition will be always true. If the condition is always true, there will be n comparisons. Okay. What about for the I equal to 2? When I will become 2, you see we are going till end, not end actually, are going till the last but not the end. So here we are going till actually we have n minus 1 comparisons. I can say that for I equal to 2. For I equal to 3, we will have n minus 2 comparisons. For I equal to 4, we will have n minus 3 comparisons. So in this way, the term is, actually, we at the term is becoming low and low, the whole value, n minus 3, n minus 4. In this way, a time will come when it will become 4 plus 3 plus 2 plus 1, like this. Am I clear? So now see, this particular arithmetic progression is representing a special function, what we call n into n minus 1 by 2, etc. The Tn, you can say, somehow the performance of this Tn is a some function of this, and what you can say, it is nothing but n by 2 minus, I'm sorry, n square by 2 minus n by 2, right? You see here, so this is your Tn. Now see, same situation arises over here. I have a quadratic class of function and so this is actually what I mean, means what, half n square minus half n, right? So this is a quadratic class of function and this is a linear class of function. We have already seen in this example that if we have a function something like this, for a very large value of n, this quadratic function will start dominating the linear one. And since we are always considering a very large value of n, that means I can say that when for n towards infinity, this half n square will be very, very large than half n. That means you can say that Tn will be something like half n square for a very large value of n. And this n square, I have a n square over here which is multiplied by this factor half, where the class of function is the square, which is just multiplied by the half. So you can delete this particular constant term. We have already seen over here in this case that you can, the C3 doesn't have any significance for very large value of n when it is n square. So you can say that this is equal to big O of n square. So that means bubble sort complexity is big O of n square. Is this clear to all of you? Tell me. And Priyanka, can you hear me? I don't know Priyanka can hear me or not. Okay, okay, fine, good. Thank you. Now, let's go for another sorting algorithm, say selection sort. Okay. In the selection sort, what we have seen? We have a say same amount, same data, suppose 2, 7, 4, 3, 9, 6, 5, suppose. What we do? We actually compare say minimum, maximum one. Suppose I want to sort in decreasing order. Okay. So what we do? We find the maximum one from this array and replace with the first one first. So this one will be converted to 9, 7. This 9 will come here and 2 will obviously go in this side. So because 9 was the maximum one. 9, 7, 4, 3, 2, 6, 5. Something like this. So assume that somehow, in case of what is the worst case scenario of this selection sort? What is the worst case scenario of selection sort? You can say that the data is given such a way that the maximum one, max value, is always at the end, right? So the max value is always at the end. So what does it mean? If the max value is at the end, then somehow we have to traverse till last, then only I can get the maximum value. If the 9 was present somewhere over here, something like that. Okay. So now, anyway, so that means if you consider for the first set, you are going for n minus 1 I mean, you are starting from here and you are going till end. I'm sorry. You are starting from this 7 and you are going till end. So basically, how many comparison you are doing for the first set? N minus 1 comparison. You are doing n minus 1 comparisons. Then you have got this 9, and then again you are checking maximum in between this two. And for this, you are starting checking from here and you are going till end. Right. So next time you are actually comparing with n minus 2 times. For the third set, obviously you will compare, you can understand this pattern, I think, n minus 3 times. And in this way it will go on decreasing, something like this. Now see, in case of selection sort, this Tn is actually following the same pattern uh, as your bubble sort was. So here only the difference is that it starts from n minus 1. Here we started from n. But here it started from n minus 1. So apparently you can say that yes, these two classes are different, two functions are different. Yes, they are different. But ultimately you will see they are not different with respect to the class of function. Because if you just write the corresponding result for this particular function, it will be what? It will be the if the limit is 1 to n, it is n into n minus 1 by 2. So here it will be n is itself n minus 1. So that means n minus 1, n minus 2 by 2. Just a minute. I think you are, is it n into n minus 1 or n into n plus 1? Just a minute. 1, 2, sorry, 2 plus 3 plus 4. That is 7, 9, 10, and 4, 8. 5 by 2. So n into n plus 1, not minus 1. So anyway, so that means here it will be n minus 1 plus 1 plus 1 by 2. By the way, here it will be n plus 1. Right, plus 1. So that means it becomes n into n minus 1 by 2. Right? This 1 and 1 cancel out. That means it becomes n square by 2 minus n by 2. So that means your Tn become half n square minus half n. So with respect to the calculation presented in this bubble sort, we have we have a different one. It is half n square plus half n. Here it is half n square minus half n. Obviously they are different. But when you will think n is equal to 10 to the power 19, at that time, with respect to this n square, this n doesn't have any significance. whether it is a plus or minus doesn't matter. We can ignore the term with lower number, with the lower value of the power. So I can say that when n is tends to infinity, Tn will be almost nearly equal to half n square. As we have seen that we can cancel this particular constant term because it is representing a quadratic class of function. So that's why I can write that Tn is again equal to big O of n square. So in case of selection sort, we can also see the complexity is Tn big O of n square. So tell me, is it, have you understood? Hello? 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 Am I audible? Hello? Am I audible? Yes, sir. Understood. Good. And what about Progga? By the way, Priyanka, এখন কি তাহলে ছেড়ে দিতে হবে? ছেড়ে দেবো? তাহলে কি ছেড়ে দেবো এখন আমি? 9:45 বেজে গেছে নাকি? প্রায় 40 বেজে গেছে। ওকে। Okay, so one thing is sure, if you compare the bubble sort and selection sort, let me conclude what we have discussed. If you compare bubble sort and in other side selection sort, if you compare, what we have found? That we found that they are basically following same class of function in worst case scene. That means there is no significant difference in using either bubble sort or selection sort for very large value of n, large input value. Both are order of n square. Okay. So with this conclusion, we can end our class for today. Uh, we will see in the next slide, in the next day. I mean, we have a you have a homework. You try to find out homework is try to find out the worst case time complexity of insertion sort. Okay, so this is your homework. So we are stopping here right now. In the next day, we will try to analyze the time complexity of other sorting algorithms. Okay, so thank you.